All right. Anyways, we talked about the natural numbers. So you said, how do we know that the natural numbers are just the things that we know them to be? Well, what do we know? The natural numbers are just, for the purposes of this class, all the numbers you can get starting with 1 and doing plus 1 as many times as you want. That's exactly what inductive gives us.
So that has to be in every inductive set. Basically.
So they, by definition, are in every inductive set. The only question that remains is, are the natural numbers themselves inductive? Do they satisfy this property?
Oh.
When we show that they satisfy this property, then that kind of gives us exactly what we're looking for.
Okay.
So let's prove that the natural numbers are inductive. So all we know so far is that they're a subset of every inductive set. Now let's prove that they are themselves inductive. So first off, we know that 1 is in every inductive set. Right? By definition of a set being inductive, it has to have 1. So 1 is in every inductive subset of R, by definition of inductive, showing that 1 is in N. Remember, N is the intersection of every inductive set. If 1 is in every inductive set, then 1 is in the intersection of every inductive set. Therefore, 1 is in N. Does the logic there make sense? Okay. Now we need to show that this property holds right here. We need to show that if x is in N, then x plus 1 is in N. And then we'll have shown that N is inductive. We need to show two things to show that N is inductive. We need to show that 1 is in N, and then we need to show that if x is in N, then x plus 1 is in N. So we've already shown this part. Now how do we show an implication? How do we prove an implication? We assume the antecedent and show that implies a conclusion. That's how we show prove conditional statements, prove implications. So I've proven this part, now I'm going to prove this part. So assume that x is in N, and I need to show that implies x plus 1 is in N. Since x is in N, what does it mean to be in N?
This is every inductive subset.
It's in every inductive set. So since x is in N, then x is in every inductive subset of R. Now if x is in an inductive subset of R, what does that mean?
X plus 1.
X plus 1 is in an inductive subset of R. Because every inductive set, I'm going to stop saying subset of R, I'm just going to call them inductive sets. So if x is in every inductive set, and since the set is inductive, then x plus 1 also has to be in every inductive set.
Isn't that what we're trying to prove?
No, we're trying to prove that N is inductive.
What is N? Oh.
N is the intersection of every inductive set.
Also, like, low-key, that's what you're saying. Like, how can you use something to prove that something?
So here's the numbers in every inductive set. So this is the intersection of all inductive sets. And then over here we have the natural numbers. Okay? First thing we said is 1 is in every inductive set. Therefore, 1 must be in the natural numbers. That was our first line of thinking. Right? Next we said, let x be some natural number. Pick one in there.
Hang on. Okay, so N being inductive means that everything in N.
We're proving N is inductive. We don't know what's
Right, I
inductive.
know. That's what I'm saying. But
Yeah, so we need to show, one, that 1 is in N. And then 2, we need to show that if x is in N, then x plus 1 is in N. So we need to show every time you pick an x in N, then x plus 1 was also in N.
Right, that makes sense.
Okay, so this is the part we still need to prove. Huh?
I'm looking for the other word. What's the one where it's like they're all natural numbers? Right?
Yeah.
Now I'm confused.
We're proving that the natural numbers is inductive.
Right. But the set of numbers that is in all of the sets, what is that set called?
So the definition of natural numbers is the intersection of every inductive set.
That is my whole point. Isn't that exactly what we're trying to prove?
No, we're using the fact that n is in every inductive set to prove that n itself is inductive.
Okay.
Make sense?
That makes sense.
So we know that 1 is in every inductive set, therefore 1 is in n. We pick some x in n. Since x is in n, that means x is in every inductive set. If x is in an inductive set, that means x plus 1 is also in it. Since x plus 1 is in every inductive set, that means x plus 1 is in n. Make sense? That's exactly what we're saying here. Assume x is a natural number. Then x is in every inductive set, which means x plus 1 is in every inductive set, which means x plus 1 is in n. Therefore, n is inductive. Yep. Okay. Now, I skipped something else I was supposed to do before I moved on to mathematical induction. I need to prove that if A is a subset of an inductive set, and A is I need to show that if an inductive set is a subset of the natural numbers, then that set is equal to the natural numbers. And it's a really small proof. If it already makes sense to you, that would make sense since it's a really small proof, but we'll write it out to be sure. If A is an inductive subset of the natural numbers, then A is equal to the natural numbers. And this should make perfect sense.
Yes.
If A is inductive, then the natural numbers are a subset of A, and if A is also a subset of the natural numbers, then they're equal. In other words, if the two sets are subsets of each other, then they're equal, and that's exactly what we're going to say. 1. Observe that A is a subset of n. How do I know that?
Because it was given.
It was given. A is an inductive subset of n. 2. Since A is inductive, n is a subset of A.
Crazy.
Therefore, A is equal to n. Nothing strange there. Pretty straightforward proof.
Yes. Okay, so I have a question.
Go ahead.
N is, it goes on to infinity, right?
Yeah.
So,
It has no largest element.
how can you have an inductive subset? Because if it's inductive, then there's 1 in there, and x plus 1 is in there. Therefore, you can never have an n.
Remember, so an inductive subset of n is just going to be n itself, is what we just proved.
Right, I'm saying you can never have an inductive subset. Ever.
Of any set?
Right.
Sure, I can. The natural numbers are a subset of the real numbers.
Okay, but
Both those are
the
inductive.
subset will always be infinity. Will always be going to.
It will never have the largest element.
Right, that's one.
That's correct.
Okay.
Okay, so now we're ready for the principle of mathematical induction, which is what we use to do proofs by induction that you guys are used to. Well, I don't know, have you ever done proof by induction? No? So you two are used to it, but you've never done it, so we'll go through it.
Wasn't there I feel like sometime in discrete math we did a proof that proved proof by induction was valid. Is that what we're doing right now?
Well, here's what we'll say, and then we'll do a proof of it. Yeah, we'll prove that you can use proof by induction. So this is going to be the principle. And then we'll do a proof that says that you can use it, and then we'll do a proof actually using it.
Okay.
Yeah. Okay, so mathematical induction, what's the principle? The principle is that if for each natural number, well, let's just read. For each natural number, let Sn be some assertion or some statement about n. If S is true, if S of 1 is true, so the assertion is true for 1, and if S being true for k implies S is true for k plus 1, for where k is some natural number, then S of n is true for every natural number. So if I have some statement, I have some statement S, and I know that S is true for 1, and I know that anytime S is true for k, that implies S is true for k plus 1, then S is true for every natural number. So my statement could be something like greater than 0. If I know that 1 is greater than 0, and I know that every time k is greater than 0, k plus 1 is greater than 0, then I know that greater than 0 applies for all natural numbers.
I have a question. So why are we only limiting this to the natural numbers? Why can't it be any inductive set?
Any inductive set? Because we're not guaranteed to get all the numbers just by doing this. If I test 1, and every time I do k plus 1, then I'm only guaranteed to have incremented over the natural numbers. So let's say I'm trying to prove that, say that S is a statement, is a whole number. And I'm trying to prove it, every real number is a whole number. Well, I checked 1, yep, that worked. And then every time it was true for 1, it was true for 1 plus 1, and that plus 1, and that plus 1, and that plus 1. That never checks 1/2.
Okay.
So if it's true for 1, and every time it's true for k, it's true for k plus 1, I'm only guaranteed to have checked all the natural numbers.
But you don't know it's true for k.
But I don't, so it's going back to, remember I say I've got some secret set A. And what do I tell you? I tell you that 1 is in A, and I tell you k in A implies k plus 1 is in A. What's the only thing you know for sure is in A?
1.
You know 1's in there, right? And then, you know, since 1's in there, 1 plus 1 is in there. So you know that 2's in there, and you know that 3's in there, and you know that 4's in there, etc. These are the only numbers that you know for sure are in A, right? Maybe there's other numbers in there, but for sure these ones are in there. So if I prove some assertion is true for 1, and I prove anytime it's true for k, it's also true for k plus 1, then I've proven it's true for these numbers, the natural numbers. It could be true for other numbers, but what I've proven is that it is true for the natural numbers.
Okay.
That's the idea behind mathematical induction. We're proving that some assertion is true for at least all the natural numbers. Could be true for other things.
Alright.
Okay. And then one more quick note, because is now the time to introduce it? No. We'll cross that bridge when we get to it. Let's not confuse it. Okay, so that's the principle of mathematical induction, and now let's prove it. So we're proving that this statement is true. Proof of induction. 1. How do I want to start by my assumption? Assume that S of n is some assertion such that S of 1 is true and if S of k is true, then S of k plus 1 is true for some k in natural numbers. Just assuming what we need to assume here to do this proof, right? What does this say? It says if I have an S that's true for 1 and every time it's true for k, it's true for k plus 1, then S of n is true for every natural number n. So I'm trying to prove that S of n is true for every natural number n using that information. So you understand what the proof is trying to do and why this is what I'm assuming? I'm assuming exactly what I had over here.
So, just really quick, why do we let 1 in there instead of letting 0?
So that's the side note I was going to get here. I'll get to that in a second, why 1's kind of an arbitrary starting spot.
Yeah.
And we could have picked somewhere else.
Yeah.
So we'll get to that in a second, but let's first wrap our heads around proof by induction. Okay. So we understand, here's the antecedent of what that is saying over there. Now we need to prove that S is true for every natural number. That's what we're doing. So, 2. Let A be the set of all, what variable do I want to use in here? I use k down there, but yeah, we can just use x. Let it be the set of all x such that S of x is true.
I got a question.
Oops. Sorry. Let me, before I answer that. A be the set of all natural numbers such that S happens to be true for that natural number.
Okay, so S is a statement about it, right?
Yeah, something like is even,
Right.
is greater than 0,
So,
is.
you're saying if the statement is true for 1, and if it's true for k,
No. If the statement is true for 1, and if it being true for k implies it's true for k plus 1,
oh,
then it's true for all natural numbers.
oh,
Good?
okay.
Yeah, we're never saying S of k is true. We're saying S of k implies S of k plus 1 is
It's
true.
So if that is true, then it's for all. Right, which makes sense.
Yeah. Okay. So let A be the set of all natural numbers that make S true. Okay? Ultimately, we're trying to show that A is every natural number, and we're done.
Right.
If A is the set of all the natural numbers that make the statement true, and A is all natural numbers, then all natural numbers make the statement true, which is what we're trying to prove. We're trying to prove S of n is true for all natural numbers. Good with big picture what we're doing? So, how are we going to prove that A is equal to all natural numbers? We're going to show that A is inductive. Because I know by definition of A, it's a subset of natural numbers. The only thing in here are natural numbers. Therefore, A is a subset of natural numbers. If I also show that A is inductive, then I know that A is equal to the natural numbers. That's this proof right here. You follow the logic there? Okay, so let's do that.
Oh, right, yeah.
3. Observe that since S of 1 is true, that 1 is in A. Right? A is a set of all natural numbers that make S true. We knew from up here, S of 1 is true. Therefore, 1 has to be in A. Is my camera still going?
Yeah.
Okay. So, good? Now we need to, so we proved the first part, now we need to let K be in A, and show that implies K plus 1 is in A. Let K in A. Should we use a different letter than K?
No?
You're good with K?
Yeah.
Alright. Then, K in A implies S of K is true, implies S of K plus 1 is true, implies K plus 1 is in A. Yeah, let's follow the logic of that real quick. So, pick something in A. Pick any element you want, doesn't matter.
1.
K. We don't know which one, it's just something.
Yeah, but all we know, let K
Pick any random thing out there. Close your eyes, pick something.
Right.
We're going to call it K.
Mm-hmm.
So we know that K is something in A. Since K is in A, what does that mean? A is a set of all natural numbers that make the assertion true. That's what A is. So if K is in A, that means S of K is true. A is the set of all natural numbers that make the assertion S true.
A is the set of all natural
Yeah, by definition, A is equal to the set of all natural numbers such that S of that natural number is true.
Right. So if K is an A, then S of K is true.
Is true, yes.
Okay.
Now, if S of K is true, S of K plus 1 is true.
Wow.
That's what S is. S is a statement that's true for 1, and every time it's true for K, it's also true for K plus 1.
Ah.
That's exactly what this is saying. We're saying let S be an assertion that we know is true for 1, and that we know every time it's true for K, it's also true for K plus 1.
We should try using a different letter.
No, that's fine, but like, what? How can you do that? So,
That's
you're assuming,
our definition of
you're
S.
assuming that it's true.
Yeah, we're assuming that S is this kind of... Back to principle of mathematical induction, this is what we're proving. We're proving that for each natural number n... Oh, let S of n be some statement about n. Okay. We're proving that if S of 1 is true, and if S of K being true implies S of K plus 1 is true, then S of n is true for every natural number. So we're assuming that we have an S such that S1 is true, and S of K being true implies S of K plus 1 is true. And we're showing that leads to S being true for every natural number.
Okay.
That's what we're proving.
So, we never proved that S of K implies S of K plus 1.
Correct, that's given to us.
How was that given to us?
We're saying
I
if...
thought that we proved that in discrete math. Like, I have a weird memory of us proving that.
We didn't go about it the same way in discrete math. We didn't have a definition of an inductive set to prove proof by induction. We did it with what we call smallest counterexample.
Right.
So once we get to proof by induction, you're going to see that it works the exact same way, but we're coming at it a very different way. We got to work up nice and slowly to it in discrete math. Here it's like thrown at you and you just got to swallow it.
Okay.
Do we do proof by smallest counterexample anywhere in this class?
I don't know.
Like I guess we could if we choose to, but
Yeah, it's logically equivalent to proof by induction, so. Anyways,
Okay.
so you're now good with S of K implies S of K plus 1.
Because it says so, yes.
Yeah, by definition of S, this is true. For the S that we were given. We know every time S of K is true, then S of K plus 1 is true. So I know K is an A, which means S of K is true. Since S of K is true by definition of S, S of K plus 1 is true. And then since S of K plus 1 is true, K plus 1 is an A. Good?
That was super simple.
Yeah,
We were
there's nothing
doing
complex
something
here.
That was easier than what I thought it was for some reason.
That's how all math feels.
not.
It's all complex until it finally clicks and you're like, that's it? That's all we were talking about?
I feel like sometimes it clicks and it's still really hard to understand.
Well, sometimes, but. For example, like talking about relations. Relations, kids have such a hard time with it, and then later when you come across it again, you're like, really? Functions is another one for some reason. They're just complex until you work with them all the time. Composition is what I mean by functions. I was thinking of composition. Composition kills kids until
Functions and
you get used to it and you're like,
that. I don't remember them being too bad.
alright, moving on. So therefore, what? What did we just prove in the above line?
Proof by induction works.
Therefore, A equals N.
Yeah.
Almost, therefore A is inductive.
Yeah.
Which means it's a subset of N.
Well, no, A was a subset of M by definition.
Yeah.
Oh yeah.
Proving that A is inductive means N's a subset of A.
Right.
And now we can use that proof up there to say, therefore, A is equal to N.
Right.
You follow the logic there? And we're done. So, proof by induction works. Now to help cement this in, let's actually do a proof by induction, because this is all kind of a high level stuff. Let's turn this, make sure I can get the whole whiteboard. Okay. So, the common first proof by induction is prove that the sum of all natural numbers.
Is this the Gauss one?
I think this is the first one I do. Sure.
Well, the one that
From j equals 1 to n.
is associated with the story of Gauss.
J is equal to. Yeah, so the story goes something along the lines of Gauss's math teacher, to keep the students busy, I don't know how young they were supposed to be, but young kids. So to keep his kids busy, he had them add up all the numbers between like 1 and 1,000, something like that. Or I think it might have been 1 and 100. Some small thing you might give a bunch of secondaries to do to keep him busy. Anyways, so Gauss came up with an answer real quick, gave the teacher's answer, and he was the only one that had the right answer, and he did it like that. And how did he do it? He realized, if you think about, we'll look at the numbers from 1 to 100 to see it. 1, 2, 3, dot, 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 all the way up to 97, 98, 99, 100. And maybe think about a 0 to start here. I don't know exactly how we thought about it, but it's going to be something like this. Notice that 100 plus 0 is 99 plus 1 is 98 plus 2 is. So you keep doing that, you're going to get 50 100s plus the 50 in the middle remaining. So that's exactly what this formula is saying. If you add up all the numbers from 1 to n, you're going to get n times n plus 1 over 2. Notice that when you plug in 100, what do you get? You get 100 times 101 over 2, right? Same thing?
Yeah.
Times top and bottom of this by 2, maybe. That will help you see it. So let's take this, and we'll multiply top and bottom by 2. What does that give us? 2 times 50 is 100. And then we already distributed the 100 in here, so you still have 100. And then 2 times this 50 is 100. And then it's all over 2 still. So I have a 100 here, I have 100 100s, and 1 100. So how many 100s do I have? I have 101 100s over 2. Oops, I wrote backwards, but you see. Right? So, that's how we did it. Something to that effect. So that's where this formula. That's one of the stories behind the formula, but the formula was known well before Gauss. You, with enough time, probably could come up with the formula just fine. Okay, so let's prove this real quick. So prove that this is true for all n in n. In other words, for any natural number you choose, adding up all the natural numbers to that n is always going to come out this way, is what we're going to prove. We just barely did it with 100, maybe that makes sense, but that doesn't guarantee that it works with 177, right? So we need to prove it's always true. So, how do we start this? 1, let A equal the set of all n in n such that the sum from j equals 1 to nj is equal to n times n plus 1 over 2. Or in other words, let A be all the natural numbers that make this assertion true. It's all the natural numbers, such that when you add up all the numbers to that natural number, you get that number times itself plus 1 over 2. Make sense what n is? Or what a is? So what we just pseudo-proved before is that 100 happens to be in this set. We're going to prove every natural number is in the set. Okay? How are we going to do that? We're going to show that this set A is inductive. Remember, we defined A, in its definition, this is important, we always make it a set of natural numbers. So A is always a subset of natural numbers. So all that ever remains to show is that the natural numbers is also a subset of A, which we get by showing that A is inductive. Make sense what we're doing? And it makes sense why all we have to do now is show that A is inductive and we're done? So that's what we're going to do. We're going to show A is inductive. How do I show that A is inductive? What's an inductive set? It's a set that contains 1, and it's a set that if it contains x, it contains x plus 1. That's what an inductive set is. So, first thing I need to do is show that 1 is in A. Now, we often call this the base case.
The base case.
Yeah, the base case. So, proof by inductions are so common that they almost have their own flavor on how people always prove them. So, if it feels like I'm proving these a little bit using conventions I don't typically use, that's because I'm not. Because proof by inductions are typically their own thing. And so you kind of let your reader know, hey, we're doing a proof by induction. So, base case. Let n equal 1. Then, so let's check if it's true for 1. Then the sum of all the numbers starting... Are you guys all okay with this notation? Sorry. You've all seen that? We're all good? Okay, cool. That saves us time. Alright, so then the sum of all the natural numbers starting at 1 all the way up to 1 for j is equal to... Let's see, what's 1 plus 2 plus 3 plus 4 all the way up to 1?
1.
It's just 1, which is the same thing, oops, which is the same thing as 1 times 2 over 2, right? Which is the same thing as 1 times 1 plus 1 over 2.
So it works.
So it works. Therefore, 1 is in A. Good? Okay, now we need to show the second part. We need to show that if x is in A, x plus 1 is in A. So assume this, show that leads to this, then you've shown the implication's true. So assume K is in A. Typically you use K's when you're doing proof by induction, so that's why I'm using K instead of X's. Assume K is in A. What does K in A mean? What does that give us?
K plus 1 is in
No, that's what we're proving.
for K.
That gives us that the sum of all the numbers starting at 1 going to K is equal to K times K plus 1 over 2. That's what it means for K to be in A.
Right.
K is a set of all natural numbers that make this assertion true. Therefore, this assertion is true for K when you plug in K for n. Make sense?
And what's the J doing?
It's just a dummy variable to say you're incrementing from here to here.
Okay.
Anyways, so I now know that the sum of all the numbers up to K is equal to this. I'm trying to prove, sometimes when you're doing a proof by induction, it's helpful to remember what you're trying to prove. And right aside. I'm trying to prove, jeez.
No, we know what you're trying to do.
Well, let's write it out explicitly. I'm trying to prove that the sum from j equals 1 to k plus 1 is equal to k plus 1 times k plus 2 all over 2. If I get to this point, I'm done. Then I know that the assertion is true for k plus 1. So I need to get from here to here. I need to manipulate this equation until I end up with this equation using valid rules. Okay?
Yeah, that's right.
So to get from this to this, what do I need to do?
You need to add k plus 1.
I need to add k plus 1. This plus k plus 1 is this, right?
Mm-hmm.
Not losing you in the notation here, or am I?
No, it looks great.
Okay, so, and what I do to one side, I need to do to the other side. So I need to show that when I add k plus 1 to this, it really is this, just in a different form. So 6. Then, the sum from j equals 1 of j to k plus 1 is equal to k times k plus 1 over 2 plus k plus 1. Everyone okay with this equation? I took this and I added k plus 1 to both sides. That's this.
Okay.
Good? Now I'm just going to keep manipulating this to get it like this. First thing I want to do is get a common denominator, so I'm going to multiply this thing by 2.
Mm-hmm.
So this is equal to k times k plus 1 plus 2k plus 1 all over 2. Nothing weird. Good? Okay, now, obviously, just factor out a k plus 1.
Mm-hmm.
So factor out the k plus 1. What am I left with?
k plus 2.
K plus 2.
Well, okay, so how is it that you added k plus 1 and, like, because you already have k, or is it just going up to k?
So I know that, coming back to here, I assume k is in A, which means that this equation is true.
Right.
For k.
Uh-huh.
I take this equation and I add k plus 1 to both sides.
Which we can do because...
You can always add the same thing to both sides of an equation.
Right.
Did we cover that in this class?
Yes, I think.
Yeah, you talked about it last time.
Okay. Yeah, so you can always add the same thing to both sides of an equation. You can always multiply the same thing to both sides of the equation. So here I have an equation. A big old sum is equal to this thing. It's just an equation. Add k plus 1 to both sides. That gives me this equation.
Mm-hmm.
And then just rewrite this like that, like that. So now I have this is equal to this, which is exactly what I wanted.
Right. Okay.
So what does 6 tell us?
Therefore,
That is
A
true for all. You showed.
You're
what
skipping.
wanted to show.
What exactly does 6 tell us?
That a is equal to n.
That k plus 1 is in A. That's what we just showed. K plus 1 satisfies the statement. That's what this says. If that is equal to that, that means the statement is true for k plus 1. So k plus 1 is in A.
Then a is equal to n, right?
Therefore, A is inductive.
And then it's
Inductive, which gives us A is equal to n because we also defined A such that it was a subset of n. So it's an inductive subset of n, so A is equal to n, and we're done. Okay? There's a proof by induction. Any questions on it? Your next homework is going to be do 50 of these, basically.
Yeah, that's what it was in discrete math too. Got really good at figuring out how to manipulate a sum.
So let's do another one. And make sure we're getting it. Oh, we don't do another one yet. So there's a flavor of it. We'll do some more, but first let's cover the rest of like book material, then we'll come back and just do examples to our heart's content.
We haven't gone over the completeness axiom yet, have we?
Now,
Is that next?
it's right around the corner. Let's actually actually just go on break since I've got to fill up the whiteboard anyways, and then when you come back, we'll continue book material. So feel free to go on break. Okay. Let's continue. All right. So we now have our definition of natural numbers. The next set that seems natural to define is the integers, and you have the intuition for what the integers are. Now we have a precise definition for what the integers are. The integers, represented by that fancy z, is a set consisting of the natural numbers, their negatives, and 0. Make sense? Pretty intuitive. Okay? And then the rationals, this fancy q, is another set that we can define. And the rationals is every quotient of integers, m over n, where n is not 0. Another way that we can write the rationals is it's equal to the set of quotients such that m and n are integers and n is not 0. Where quotient is defined exactly how we have it defined over here. So we know what that symbol means. So back to very precise language, not doing examples, we know exactly what all these things mean. Right?
When do we start proving, when do we prove that the inverse, that the multiplicative inverse is a specific number?
We already did.
I mean, but like, showing that it's the reciprocal.
What do you mean that's a reciprocal?
So, y inverse is 1 over y. When do we prove that?
Ah, well, you can prove that really quick if you want. 1 times y inverse, by definition, is 1 over y, where y is not 0.
Okay. Sonic? I don't know. It's not exactly what I was wondering.
Well, maybe you were looking for 1 inverse is equal to 1 times y inverse is equal to 1 over y. Anyways, so all the way up to the natural numbers. Now, we'll notice something. So, the natural numbers now are the first set that we're talking about, that we have defined here, that satisfy all the field axioms and all the positivity axioms. Notice that these do not hold for the natural numbers, and they don't hold for the integers. How do I know that the field axioms don't hold for the natural numbers?
Because the natural numbers don't have negative numbers.
Because you can't find the additive inverse, exactly. Remember, one of the axioms is, let's see, right here. For every x there exists a y such that their sum is 0. That is not true for the natural numbers. Pick 2. 2 is a natural number. What's a natural number I can add to 2 to get 0? I can't. So the natural numbers do not satisfy these field axioms. Let's look at the integers. Do the integers satisfy these field axioms?
No.
Yes.
There's not always a multiplicative inverse.
We don't have the multiplicative inverse. Looking at this one. For every number that's not 0, there exists some other number such that the product is 1. What is a number I can multiply, what's the integer I can multiply 2 by to get 1? There isn't one, right? And so, the rationals are the first set that we're talking about that satisfies every single one of these and satisfies both these.
The rationals?
The rationals, all the fractions.
Wow.
Is a sum, doesn't matter what order I add, thank you. Does it matter what order I add rationals? No, so that works. Is adding on the rationals associative? Yeah. Is there a 0 element in the rationals? Oh, here's another problem with the naturals. No 0 in there. Do I always have an additive inverse in the rationals? Yeah. Can I multiply numbers in the rationals in any order? Yeah. Are they associative by multiplication? Yeah. Is there a 1 in there that does this? Yeah. Do I always have a multiplicative inverse as long as it's not 0? Yeah. Can I distribute? Yeah. Is 1 a different number than 0? Yeah. So it satisfies all those. What about these? If x and y are positive, x plus y and x times y positive? Yeah, satisfies those. Is it true that every rational is either this or this or this? Yeah. So the rationals completely satisfy all our axioms, yet you know that this class is real analysis, and so we're somehow talking about the real numbers, not just the rational numbers. And so there's still a gap and we're still missing something. In other words, these axioms alone are not enough to ensure we're talking about the real numbers. These don't guarantee us that we have the real numbers. We could just be talking about the rational numbers if we just continue from here on out, looking at just the logical implications of these axioms. Then everything we're talking about is true for just the rationals. What ensures us that we have the reals? And why do we care? Why do we need the real numbers? Because one of the things that we're very much interested in analysis would be something like, when is the polynomial x squared minus 2 equal to 0?
Right. That's an irrational number.
This is a question that you'd very naturally be interested in. And notice that we know that sometimes this is negative, sometimes this is positive. Is it true that this is ever equal to 0?
Yeah.
So plug in, for example, 0 in for x, what do we get?
You get -2.
Negative 2, which is less than 0. So let's just look at this, forget the equation for a second. Let's look at this polynomial. Look at this polynomial. When I plug in 0, I get -2. When I plug in 2, I get 2. So I know that this polynomial is sometimes a negative number. I know that this polynomial is sometimes a positive number. Is it ever 0?
Yeah.
Not if we limit ourselves to the rationals.
Right.
If we limit ourselves to the rationals, then we can never find, for something this simple, we can't say that this is ever equal to 0. If all we're interested in is the rationals. And we very much would be interested in where this is equal to 0. That's something very simple that we'd want to be able to, we'd want our system of math to be able to answer a question like that. So, as great as all these axioms are and what they give us, they still don't give us everything that we need to do the analysis that we want to do. And so we still need one more axiom to get the real numbers. But first off, before we do that, let's prove that I'm not lying to you. Let's prove that this has no solution. Or in other words, what are we proving? We're proving that the square root of 2 is not rational. It's not in Q. Whatever that number is that satisfies this equation, it is not in Q. That's what we're going to prove. So we're going to prove that the square root of 2 is irrational or not rational, same thing, to show that the rationals can't even allow us to solve simple things like this. Then we'll come back with our one more axiom, the completeness axiom, which will give us the real numbers, and then we'll continue on our way with the real numbers. That's big picture how we're going to continue for the rest of class. Make sense?
And will we be constructing a definition for exponents this class?
I don't know. I think we now have x to the n. I'll have to go check in the book. Maybe it still comes up later, and he's just letting us use squared because it came up before. But x to the n is ultimately going to be x times n times.
Right. Is there a more precise way of writing that?
Using product notation. From j equals 1 to n of x is x to the n. Instead of summation notation.
Alright.
Just taking the product of all of them. So that will ultimately be our definition for natural number exponents, but that doesn't answer the question of rational exponents and 0, x to the 0. So we'll have more of that conversation later in the class. But anyways, continuing. Jeez. So next thing we're going to focus on is proving that the square root of 2 is irrational. And there's a couple definitions we need along the way and a couple things we need to prove along the way. Those of you who did discrete math have already seen these. So hopefully not too weird. And then M is quick, so we'll be through this in no time. Alright, so first off the definition, divides. If I have two integers AB, A divides B means that there exists some integer C such that A times C equals B. So I say that, how do I know that 2 divides 8? I know 2 divides 8, or 2 goes into 8 evenly, is the way some kids like to say it. 2 divides 8, I know that that's true because there exists an integer, namely 4, such that 2 times 4 is 8. Make sense? Then our definition of even. An integer is even provided that it's divisible by 2. Pretty straightforward. You remember these definitions? Bit of a throwback. Next definition. An integer is odd provided that there exists some other integer such that I can express a as 2x plus 1. So let's see some examples of that real quick. We know, for example, that 17 is odd. How do I know that 17 is odd? How would I prove 17 is odd? Because I know it's 2 times 8 plus 1. Since I can express it as 2 times an integer plus 1, then it's odd. If I can't express it this way, then it's not odd. So we know intuitively, this isn't a proof, but we know intuitively that 16 is not, because 2 times that plus 1, there's no integer I can plug in there that makes this true. Right? So that's why 16 is not odd, yet 17 is odd. So we good with these three definitions: divisible, even, and odd. Notice using the definition of divisibility, we could also say a number is even provided that there exists x such that a is equal to 2x. If I can say a is equal to 2 times an integer, that's the same thing as saying a is divisible by 2, or 2 divides a, right? So if I can write it as 2x, it's even. If I can write it as 2x plus 1, it's odd, where x is an integer. Make sense? Any weird questions on those? Ready to prove some stuff with it? All right, so let's do some basic proofs. Let's prove that the product of two evens is even. Okay. 1. Let A be in Z such that A and B are even. Okay, so I know that A and B are even. What does that give me?
Gives you that there exists a C and a D, that you can multiply them by 2 to get A and B.
Right, so we'll write down a couple more steps in that. Then I know 2 divides A and 2 divides B. 3. Then there exist two integers, x and y, such that A is equal to 2x and B is equal to 2y. Good up to there? Okay, now remember what I was trying to prove. I'm trying to prove that their product is even. So let's look at what the product is. Then A times B is equal to 2A times 2B is equal to 2 times 2. Oh, thank you. Yeah, just using A's and B's over and over again. Need my X and Y's. This marker's kind of dying. Try a different one. So A times B is equal to, that was even worse.
How does this happen in the course of 1 week?
Okay, so A times B is equal to 2x times 2y is equal to 2 times x times y.
Right.
Which gives us that 2 divides A times B. Since 2 times an integer is equal to A times B, then 2 divides A times B.
Don't we need to do a proof that an integer times an integer is also an integer?
Yes. You guys are proving that in your homework.
Dang.
That's going to be an inductive proof. Proving that the sum of integers is an integer and the product of integers is an integer.
How do you prove that?
I don't know. I've never had to do it. No teacher's been that mean to me.
Making us do all the easy ones in class.
Yeah. That's the way teaching goes. Sometimes that's the way writing a textbook goes. And it's left to the student as an exercise to prove this theorem and then continue on our way.
I don't want to do that one, make the student do it.
Yeah. Any questions about this proof?
Oh, yeah.
Oh, and 5, therefore it's even. 5, therefore A times B is even. Good? Okay, now let's prove that the product of two odds is odd. You want to get me a marker while I do this, since you're probably good with this proof? Okay, proving that the product of two odds is odd. 1. Let A and B be odd. Maybe we'll specify real quick. Only integers are even and odd, so if I say it's odd, it automatically is an integer. Down here I said let A and B be two integers such that A and B are even is kind of redundant. Only even and odd numbers are integers. What do we mean by even? Well, we kind of specified an integer is even. So, anyways, sometimes I'll be lazy and just say even or odd. Anytime we say even or odd, it's understood we're talking about integers. So let A and B be odd integers. Then what do we know? Then there must exist two other integers such that A is equal to 2x plus 1 and B is equal to 2y plus 1. Right? If A is odd, then I can express it this way for some integer x, and if B is odd, then I can express it this way for some integer y. Right? Now remember, what are we trying to prove? That their product is odd. So I'm interested in what A times B is. I need to show that that is odd. Then A times B is equal to 2x plus 1 times 2y plus 1, which is equal to 4xy plus 2x plus 2y plus 1. Any questions on the algebra there?
Sure.
2x times 2y is 4xy. 2x times 1 is 2x. 1 times 2y is 2y. And then 1 times 1 is 1.
So down there, 2x times 2y is just 4y. Or 4xy.
4xy, yeah, we could have done it that way.
Right, with you, right.
I was just explicitly writing it 2 times an integer to see that 2 divides it. Okay, so similarly, we need to rewrite this so that it's 2 times an integer plus 1. So we need to somehow rewrite all this as 2 times an integer, because we already have our plus 1. So how can we rewrite this as 2 times an integer? Just factor 2 out of everything. So this is 2 times 2xy plus x plus y. That's rewriting all this, and then we have our plus 1. And then, so, since it can be expressed as 2 times an integer plus 1, therefore, A times B is odd. Okay? So, now we need to prove that all integers are either even or odd. Good? A lot of work working up to just proving that the square root 2 is irrational. I don't want to do this one without Levi, so we'll just erase and rewrite it up there. Oh, it's already back. Oh, wow.
Christmas.
That's barely Christmas.
She said that you can just put them in the desk or something so that they don't disappear or get
Yeah, I'll hide them.
dried out.
Oh, is that an eraser?
It is.
Wow. We have a bias for just using new stuff, so may as well indulge it. Okay. So what we're doing, okay. So now proof all integers are even or odd. Okay, so now this one is going to be a proof by induction. And this one's going to be a little bit weird for those of you not comfortable with, or for those of you who have done a bunch of proof by induction, because it's not going to look how proof by inductive proofs typically look. Oh, no, it's not.
Yeah, I was like, huh?
Forget what I said.
We didn't, yeah, it didn't feel like that because last year we did this right at the beginning of the year. Yeah. It was like second or third week of class.
Well, alright then. Okay, so we need to prove that every integer is even or odd. So first thing we need to do is grab an integer and then show that it's even or odd. So 1, let x be any arbitrary integer. Now the fact that I know x is an integer, what does that tell me?
Even or odd.
No.
I don't know.
What do we know about integers?
Well, we know that the product of two
We'll prove that the product of two integers is an integer, the sum of two integers is an integer. But what do I know about x just by knowing it's an integer?
Well, it's either a natural number or a negative number or zero. A negative natural number.
Perfect! So, since I know x is an integer, I know one of three things is true. Either x is a natural number, x is negative is a natural number, or x is 0. What's our definition of integers? Z, the set of all integers, is a set consisting of all the naturals, their negatives, and 0. That's what the integers are. So if I know that x is an integer, it satisfies one of those three cases.
Why does that matter?
Because I need to prove
What's the definition?
if this is the case, it's even or odd. If this is the case, it's even or odd. If this is the case, it's even or odd. And therefore, every integer is even or odd. And maybe it would be helpful to just do like a lemma, saying all natural numbers are even or odd, and then come back and do the integers.
We're going to do the same thing you play.
Yeah, so let's just do that. It will just make it more bite-sized. Let's prove.
Whoa.
Yeah, that erases a lot better.
We should probably clean the board before we destroy it.
Yeah.
Well, it's going to happen anyways.
Huh?
I mean, whatever they put on here is what they put on here. Whoever the students are that cleaned it. We haven't used it since they cleaned it. So, anyways, prove all naturals are even or odd. Alright, 1. Let x in n. 2, let's see how I want to do this.
Why don't we just stick with the integers?
It'd be the same
Oh, I have to do this anyways. Sorry. The lemma is to prove that every natural number is even or odd. That I do by induction, and then I prove every integer is even or odd. So no wonder. I was wondering how on earth I did this, not by proof by induction. Because I already had this to fall back on. So I just was looking in the wrong place in my notes. Alright. Prove every natural number is even or odd. Alright. So something along the lines of let A equal the set of all k in n such that k is even or odd.
Maybe what we proved was that integers are either even or odd, but not both.
Yeah,
That's what we're doing.
Is that
no.
something else? Maybe we did add them in something else. We didn't have.
Oh, we proved, okay. We proved that a natural number can't be even and odd.
Yeah, that's what it was.
Okay. And we'll skip that one this class. I think that's homework. Proving that a number can't be both even or odd and still be a natural number. It's real easy. It just ends up showing it's a fraction,
Yeah, that was
which
pretty easy.
isn't natural.
Which is a natural.
It ends up, you could lead to something like 1/2 being a natural number. Okay. Anyways, continue with this. So let A be the set of all natural numbers that are either even or odd. So base case for n equal to 1, then n is equal to 2 times 0 plus 1, which implies n is odd. Right? Therefore, 1 is in A because it's odd. Alright? 4. Assume K is in A. Now remember, if K is in A, what do we know? K is even or odd. And we need to use the fact that K is even or odd to prove that K plus 1 is even or odd. If, maybe specify that in our proof right here. So assume K in A, which gives us that K is even or odd. Good? 5. If K is even, then there exists, we weren't using X anywhere already. Then there exists X in Z such that K is equal to 2X, which gives K plus 1 is equal to 2X plus 1, which gives K plus 1 is in A. A lot of logic in one go, but I think you can follow it all. If K is even, then there exists some integer X such that K is equal to 2X, right? And if K is equal to 2X, then K plus 1 is equal to 2X plus 1, which means K plus 1 is what? Odd. So since it's odd, it's in A, because A is all the natural numbers that are even or odd. So that is if X is even, or if K is even. 6. If K is odd, then there exists X in Z such that K is equal to 2X plus 1, which gives K plus 1 is equal to 2X plus 2, which gives K plus 1 is equal to 2X plus 1, which gives,
No, that's good, right?
which gives K plus 1 is even, which gives K plus 1 in A. Right? Anything weird?
Is that the end of it?
Well, almost. There's a little bit of side proof. Therefore, in either case, K plus 1 is in A. Therefore, A is inductive. Therefore, A is inductive, which gives A is equal to the set of all natural numbers, and that's what we were trying to prove. Every natural number is either even or odd. Okay?
That doesn't seem right.
Well, it feels weird.
Oh, hang on. Never mind, that makes no sense.
Okay.
Do we need to find a line in there to say that there's no numbers that aren't even and aren't odd? Because we considered if it's even or if it's odd, but what if it's not either?
So, K was a set of all natural numbers that are even or odd.
Oh,
Or not K is the set. A is the set of all natural numbers that are even or odd.
okay.
We showed 1's in there.
Oh.
We showed anytime K's in there, K's plus 1's in there. Therefore, every natural number's in there.
Oh, okay.
So maybe there is some number like that, but whatever numbers are like that didn't make it in this set, and every natural number made it in the set, therefore every natural number is.
Right.
Okay. So now we'll do it for integers. And we'll keep our definition of integers up there so that we can reference it. Okay. Prove all integers are even or odd. 1. Let x in Z. 2. Then x is in N, or exclusive or negative x is in N, or x is equal to 0. One of those three cases has to be true for x if x is an integer. Either it's natural, or its negative is natural, or x is 0. And we're going to show that in all three of those cases, x is even or odd. Make sense, big picture, what we're doing? Okay. So let's just handle it case by case. If x in N, then we're done. That's what we proved over there. If x is equal to 0, then x is equal to 2 times 0 gives x is even. So we handled the case where x is a natural number, we handled the case where x is 0. Now we need to handle the case where negative n is a natural number. If negative x is in N, then negative x is even or odd. And we'll kind of do an indented if here, kind of weird since we're doing an if within an if. If negative x is even, that means that there exists y such that negative x is equal to 2y, right?
How do we know it's even or odd? Because it's...
We don't. I'm handling the case where it's even. So I'm going to show that if negative x is even, then x is even. And if negative x is odd, then x is odd, and therefore x is even or odd.
What if it's neither or both? Don't we have to cover those cases?
No, because I know that negative x is a natural number, and I know every natural number is even or odd.
Oh, right.
So I know negative, I'm using the fact that I know that negative x is even or odd to show that x is even or odd.
Right.
Once I do that, I'm done.
Right.
Because we had 1 of 3 cases. Remember, we need to show that if x is a natural number, it's even or odd. We need to show that x is 0, it's even or odd. And we need to show that if x is a number such that its negative is a natural number, then x is still even or odd. Because one of those 3 cases are true if x is an integer. We handle all those cases, we've shown that every integer is even or odd. Make sense?
Number 4, we never proved that it was odd.
No, we haven't yet. Oh, we proved that 0 is even. That's what we're showing here.
Don't we have to do both?
No, we showed if I know that 0 is even, then I know it's even or odd.
Because it's 4.
Yeah,
But
it can't be even and odd.
Why not just prove that all integers are even or odd and not both?
And not both?
Yes.
Well, because we left the and not both to you for naturals, and so that could have been part of this. What can we do for you?
I am looking for something.
Oh, she's in room 2.
Hey,
Room 2, right?
yeah.
Yeah. Okay. So, if negative x is even, then there exists some y such that negative x is equal to 2y, right? Which gives us that, I'm just going to keep going in one long line of implication till we're done. Which gives us, if negative x is equal to 2y, what does x equal?
It equals -2y.
Negative 2y, right? We know we can always multiply both sides of a multiplication or of an equality by the same number. In this case, -1. So that leaves us with x is equal to -2y.
Which is 2 times -y.
Yeah, which is 2 times -y, which gives x is even. So if negative x is even, then x is even. Good?
Now we do odd, right?
Now if negative x is odd, and then we'll be done. If negative x is odd, that implies that there exists some y such that negative x is equal to 2y plus 1. Right? Same thing, we're going to multiply both sides by -1. So that gives us that x is equal to 2y minus 1. Right?
No.
-2y.
I'm multiplying both sides by -1.
So you need -2y.
-2y, thank you. -2y minus 1. Okay, now are we good?
Mm-hmm.
Any questions? Alright, and then that gives us that x is equal to, how can I make sure that you see this best? -2y minus 2 plus 1.
Okay.
Notice I rewrote -1 a fancy way,
Yeah.
which gives us
Wait, what?
-1 is the same thing as -2 plus 1. You good with that?
That's crappy. Okay.
And then that gives us x is equal to 2 times x is equal to 2 times -y minus 1 plus 1.
Yep.
Right? Just factor a 2 out of these two terms,
Mm-hmm.
which gives us x is odd. And we're done.
Which gives us -x is odd, right?
No.
We already did negative x, no.
Remember what we're trying to prove. Here's
Oh,
x, it's some integer.
Right.
We're trying to prove that no matter what, x is even or odd. We don't care about what negative x is. We used the fact that we knew that negative x was even or odd to prove that x is even or odd.
Right.
But we were trying to prove that this is even or odd. We didn't care about its additive inverse. Therefore, blah, 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 we're done. Therefore, x is even or odd. And we'll assume that we also did the proofs to show that, and it's not both. That's a lot simpler. I want to do this one because I want to do this proof by induction to show you more proof by induction. Okay? So now, I think we're ready to prove that the square root of 2 is irrational. Homework, we assume solutions, I was just saying we assumed that the naturals are closed under addition and multiplication since you're going to prove that. Let me see, I have 2 more notes on something that I may make you guys prove. Just get the clear board. I don't think we'll need that definition anymore. So let's see, I say that I have as an exercise for you guys to prove that anytime, prove that for all x in the rationals, where x is equal to m over n, then m or n can be expressed as an odd.
Right.
In other words, if you have an even over an even, you can always factor out a 2. And you can keep doing that until you have one of them is an odd. Either the numerator or the denominator is an odd for any fraction like that. And then I also say that I have you prove n is even implies n squared is even. Although we basically already did that. An even times an even is even, so we already proved that, so that's kind of dumb that I have you do that. But that's what my notes here say, so maybe I'm lying. Alright, anyways, now we're ready for our proof. Proof that the square root of 2 is not in the rationals, and our definition of irrational is not in the rationals. That's what we mean by irrational. So when people say the square root of 2 is irrational, they're just saying this exact statement.
So
Make sense?
we need to go prove those top two statements.
And we're using square root of 2 because I'm assuming you already know what square root of 2 is. It's the number such that when you multiply it by itself, you get 2. Right?
What's the definition of the rationals?
It can be expressed as an integer over an integer,
That's the only definition?
where the denominator is not 0.
That's the only definition?
That's it. That's all
So
irrational
all we
is.
have to do is,
Show that it can't be expressed that way.
or can.
It can't. That's what we're going to prove.
You put it over 1.
Then it's not an integer over an integer. This isn't an integer.
So you have to prove it's not an integer.
Well, if it's not rational, it's definitely not an integer because every integer is irrational.
We can't prove that it's rational until we prove that it's not an integer.
Yeah, we can.
How?
If we prove it's not rational, then we also proved it's not an integer, and we also proved it's
How
not
do we
natural.
prove that it's not rational?
That's what we're doing.
How?
Just watch.
I'm starting.
Just say it like real fast.
I can't say it real fast. It's not, it's a 7-line proof. Oh, alright.
No, I'm interested in this.
1.
I just want to understand.
Assume, by way of contradiction, that the square root of 2 is irrational. Now, what does it mean for the square root of 2 to be rational?
It can be expressed as a fraction.
Yeah, then there exists 2 integers. Then there exists m, n in z, such that m over n is equal to the square root of 2, and n is not equal to 0. So I can find 2 integers, m and n, equal to the square root of 2, such that n is not 0. Right? Furthermore, I can require m or n is odd. That's using this,
Because we supposedly proved it.
because we supposedly proved it.
What are we actually? So we're going to prove that in homework? Is that
Yeah.
what we're doing?
You're going to do that on exercise 26
And
of 1.3. Oh, so he's deferring proving this part until down the road a little bit,
why not just prove it right now?
Yeah, why not?
because it's your homework. I can't prove your homework for you. Otherwise, I'll just come back and I'll watch it, and then you won't do your homework. Okay. So, are we good with the idea that we can require that either m or n is odd?
No. Oh,
We're just going to
I'm
assume
not good with
Okay, so let's go over the very top line. So we're saying anytime you have a fraction, you can keep reducing it until one of the two numbers is odd. So let's start out with something.
Right.
Let's say we have 16 over, I don't know, 10. That's an even over an even. And what you're proving up here is, well, then this can be rewritten as 8 over 5. Okay, we got one of them odd. So anytime you have an even over an even, you can reduce it, essentially, until the denominator or the numerator is odd. Once you have an even and an odd, I can't necessarily reduce it anymore. But if they're both even, I can for sure reduce it again until at least one of them is odd. Possibly both odd, but at least one. So that's what we're saying up here. We're saying every rational number, you can get to the point where either the numerator or the denominator is odd. And still have the same rational number. So I'm saying, assume that the square root of 2 is irrational. So that means that I can say it's equal to m over n, where n's not 0, obviously, and where m or n is odd. At least one of them is odd. Possibly both, but at least one. Now I'm going to show that these equaling this is going to make them both even. That's ultimately where we're going. Okay. Since m over n is equal to the square root of 2, that gives me m squared over n squared is equal to 2, squaring both sides. Multiplying both sides by themselves, since they're equal, perfectly valid. Multiply both sides by the same number.
Squaring both sides.
Yeah, but I want you to understand why squaring both sides is a valid operation. It's because you're really multiplying both sides by the exact same number. I multiplied this side by m over n, and I multiplied this side by m over n. It's just that m over n is also equal to the square root of 2. That's why you can square both sides. Make sense?
Mm-hmm.
Okay. Which gives me that m squared is equal to 2n squared, which gives me that m squared is even, which gives me that m is even. Maybe that's what I have you do. Maybe I just wrote this wrong in my notes. Maybe I have you prove that n squared is even implies n is even.
It's just as easy, isn't it?
It's pretty easy.
What did it say before?
If n is even, then n squared is even. But we need the other direction. If n squared is even, then n is even. So take n, you know it's either even or odd. If it's odd, then squaring it gives you an odd. Therefore, it has to be even. There, I just did it for you. Don't go back and watch the video. Okay. Anyways, so m squared is even means m is even. Were you good with that?
Yeah.
And since m is even, that means n is odd. M or n is odd.
Right. But no, never mind.
Good? Since, let's see, what did we just prove is even? Since m is even, then there exists some integer, we'll call it k, such that m is equal to 2k, which gives us that m squared is equal to 4k squared, which gives us that 4k squared, well, maybe we'll stop right there and just go to a new line.
Hang on, that's kind of confusing.
Yeah, that's why I'm going to stop and go to a new line. Okay,
I mean, even just that.
I know. That's why I mean to stop and explain. So we know that m is even, right?
Yes.
So that means there's some integer k such that m equals 2k.
Right.
So that means m squared is equal to 4k squared.
Right.
Right? Okay, now I'm just going to go and substitute that right here.
Wait a minute. Why isn't it just 2k squared?
What's 2 times 2?
Yeah, but it's squared.
And what's k times k? I'm taking this and multiplying it by itself. 2k times 2k is 4k squared.
Okay.
Good? Because
I haven't
4.
messed with squares
I
in a
know.
long time.
So let's just write out. 2k squared is equal to 2 squared times k squared is equal to 4k squared.
I forgot that like once you square it, you have to keep the square. You know?
For the k's. Okay, moving on. Then, so we know that m squared is equal to 4k squared. We're going to substitute that right here. Ultimately, here's where my contradiction is coming from. I said, since this is the case, then n is odd. And now I'm going to use some information to show that n is even. N is odd and n is even is going to be my contradiction. So that's where we're going. In case it feels unmotivated what I'm doing. So subbing back in what I know that m squared is, 4k squared, into this equation, and I'm going to show that n's even, ultimately. So then, 4k squared is equal to 2n squared, which gives me that 2k squared is equal to n squared, which gives me that n squared is even, which gives me that n is even. Good with all that?
Yes.
7, therefore, square root 2 is not in Q. It's irrational.
Because n is even and n is odd.
Yeah, allowing it to be rational means that we can express it as a quotient such that the numerator and denominator are always even, doesn't matter how much you reduce it. Right?
Which is impossible.
Which isn't possible. Okay, so there's that the square root of 2 is irrational. Any questions there? So close. A lot of proofs. So that was all just to motivate the idea that, yes, in fact, we do need the completeness axiom to handle simple things like square root of 2. So now we'll start working our way up to the completeness axiom. In order to understand it, we need a definition. A non-empty set S of real numbers is said to be bounded provided that there exists some C in R such that for all x in S, x is less than or equal to C. So this might seem like a mouthful, but the concept's pretty simple. If I have some set of real numbers, and I can find some C that's greater than or equal to every number in that set, then that set is bounded. So, quick question. Let's look at the interval -27 to 51, including 51. Is that a bounded set?
Yes.
How do I know it's bounded?
Well, because you need 52.
52. 52 is a number bigger than everything in this set. It's greater than or equal to everything in this set. So 52 is some number greater than or equal to every x where x is a member of the set. This was a set S following this definition. Right?
Even 51.
Yeah, 51 also works. 2,564 also works. 86 million also works.
So, is that,
All we know is that
that's the definition?
if the set is bounded, then there is some number greater than or equal to every element in the set.
Is there a lower bound? That looks like,
That's going to be the completeness. Oh, yeah, we'll get there.
because that seems like.
Oh, yeah,
that's
sorry.
an upper bound, right?
Bounded above. Yes. Above. Provided that. Thank you. Okay, so now we get to the completeness axiom. Suppose that S is a non-empty set of real numbers bounded from above. Then, among the set of upper bounds for S, comma, there is a least element or something to that effect. There is a smallest or least bound. There is a smallest, comma, or least upper bound. Okay. So here's our last axiom that we'll need for this class, and let's make sense of what it's saying. For any non-empty set of real numbers you have, 1, 2, 3, doesn't matter what it is. For any non-empty set of real numbers that is bounded from above. Notice this one's bounded from above. Right? Let's look at an infinite one rather than one that was screen. So let's look at all the numbers from 1 to 51. Right? There's infinite things. This thing's bounded from above, right?
Mm-hmm.
What's it bounded from above by?
51. Well,
51 is bigger than everything else in here. What else?
anything above 51.
Any number bigger than 51. So if this is our S, then the set of all upper bounds for this is this.
Right.
If this is S, then any number in here is an upper bound for this thing. Right? What
why
the...
is 51 included?
Is 51 bigger than everything in here?
It's not bigger than 51.
51's not in here. Remember, the open means don't include 51.
Not only that, but that's
It means,
every.
so what does this set mean? This means
What
all the x, where x is between 1 and 51, not included.
So, oh, right.
This one is all the x greater than or equal to 51. So all the x greater than or equal to 51 are bigger than all these x.
Doesn't our definition state that it can be equal though?
Yeah. So, everything in here is an upper bound for everything in here. What our axiom guarantees us is when you look at the set of all upper bounds for some given set, for some bounded set, this thing always has a least element. We call it the least upper bound, or we call it the supremum. I'm going to accidentally call it supremum before we introduce that word because you'll get used to calling it the supremum too. So the supremum is of a set. If a set's bounded from above, the supremum of the set is the least upper bound of the set. Right? Notice, for example, what is the least upper bound of this set? What is the smallest number greater than or equal to everything in this set? 51. Now look at this set. What is the smallest number greater than or equal to everything in the set?
51.
51. This set and this set both have the same supremum. There is one number, there's one and only one number, that's the smallest upper bound of everything in this set. Similarly, there's one and only one number that's the smallest upper bound of everything in this set, the supremum.
Even though they're not the same set.
And even though they're different sets, it happens to be an identical number.
Interesting.
51. It is interesting. So, when we look at all the numbers, x such that x squared is less than 2. Here's a set. What does this look like on the number line really quick? Let's plot it out. So, 0's in here, right? 0 squared is less than 2, so 0's in there. We'll put 1 on here, negative 1 on here, 2 on here, negative 2 on here. Is 2 in here?
Yeah.
2 squared is less than
Sorry,
2?
I thought you were saying 1. No.
No. Is 1 in there? Yeah, 1's in there. Is everything between 0 and 1 in there?
Yeah.
Yeah, all these are in there for sure. And what about negative 1? Is negative 1 in there?
Yeah.
Yeah. So notice it's going to be all the numbers up to, but not including, the square root of 2.
Right.
So it's going to be up to, but not including the square root of 2. And down to, but not including negative square root of 2. Right? So this set, when you draw on the number line, looks like this. What does our least upper bound, what does our completeness axiom tell us? It tells us that this set has a number that is the least upper bound of this set. We're guaranteed that there's a real number that is the least upper bound of this set, which in this case is going to be square root of 2.
So,
This is high-level intuition. We're not proving anything right now. I'm just trying to help you see how the completeness axiom is now giving us things like the square root of 2.
that's what I was wondering. I was reading through this and I was like, I read the axioms, like, how does that help me?
Right, it seems so unmotivated. Like, what on earth does a least upper bound for a set have to do with something like the square root of 2? And here's where it comes from. Or here's the intuition for how that suddenly starts giving us more numbers.
So what's the least upper bound then?
What is the smallest number that's bigger than everything in the set?
Negative root 2?
That's bigger than or equal to everything in the set?
Square root of 2.
Square root of 2, even though square root of 2 is not in this set. Notice square root of 2 squared is 2, is not less than 2. So square root of 2 is not in this set.
It's equal to 2.
Because it's equal to 2. But the square root of 2 is the least upper bound of this set. So whatever our set of numbers are, they have to satisfy all these axioms. They also have to satisfy this axiom. Which means that a set like this has to have a least upper bound, which is going to give us our square root of 2.
And all of
I'm not proving it, so if you're thinking, how do you show that? We haven't proven anything yet. I'm just giving you intuition for what this axiom is giving us. Make sense?
It's so weird, but yeah.
It is weird. So we call the least upper bound the supremum. That's what I'm going to call it over and over again from here on out. So just somehow make that make sense in your head. Supremum, least upper bound. Can't talk anymore. I don't want to write out the other two definitions, so I'll just tell it to you real quick. A non-empty set of real numbers is said to be bounded below, provided that there exists some C less than or equal to everything in the set. I don't need to write that out, you understand that? Or maybe I'll just change this definition. Bounded below, and we switch the inequality around. So bounded below, and that's going to be C is less than or equal to all x in the set. So that's what we mean by bounded below, bounded above, flip the inequality around. Okay.
And what's the supremum of that,
And then
in a way?
this infimum, we haven't proved that there's an infimum yet, but the infimum is the greatest lower bound.
Right.
So the supremum is the least upper bound. The supremum is the smallest number we can get that's still above it. The infimum is the biggest number we can get that's still below it. That's going to be our terminology. We're going to prove that there's an infimum. The fact that there's always a supremum is going to guarantee us that there's also always an infimum. That's something that we're going to prove. And
Wait, how can that be true? Can't you have a set from negative infinity to 2?
then it's not bounded from below.
Right. So even though it has a supremum, it doesn't
this-
have an infimum.
Right, that's not what I meant.
Oh.
So this tells us that every non-empty set bounded from above has a supremum.
Right.
It's going to imply that every non-empty set bounded from below has an infimum. So if you have a lower bound, you have a greatest lower bound. If you have an upper bound, you have a least upper bound. That's what the completeness axiom is giving us.
Why do you need to prove that? It seems pretty.
Well, we have this one for free, now I need to prove it for the lower bound. Prove that there's an infimum. But let's see what we're doing here first. Let C be a positive number, then there exists one and only one positive number such that x squared is equal to C. But I use what you do in exercise 17 to do that.
That's fine. No problem there.
That doesn't seem all that motivated, but we'll go through it real quick. Cover that, okay. So, proof. Let C be a positive real number. Notation, we put the plus sign up next to the reals to say a positive real. You'll also see that with rationals and integers if you want to specify it's positive. So let C be a positive real number. Then there exists one and only one positive real number such that that number squared is equal to C. So if C is a positive number like 2, then there's one and only one positive number, that's the square root of 2. Make sense?
Mm-hmm.
So we're saying that this has one and only one positive solution, in other words. And let's see what I say here. I say 1 by exercise 17, we know that there exists an x in R such that x squared is equal to C. So exercise 17 is proving that this has a solution. Now we're going to prove that there's one and only one positive solution. I think I'm supposed to say positive solution. I'm missing my plus here. Because there's two solutions, but only one positive one. Make sense? Okay, so now to prove that there's only one positive solution, we assume that there's two. Assume, by way of contradiction, that there exists a b in the positive reals such that a squared is equal to c, and b squared is equal to c, and a is not equal to b. Two different solutions. squared minus b squared is equal to what?
C squared.
No. The difference of them. I know a squared is equal to c and I know b squared is equal to c. So that's equal to c minus c, which is equal to 0.
Right.
Right?
Which means a,
And then I can also factor this. So I can write this as a plus b, since it's a difference of squares, a minus b is equal to 0. Right? Remember, I'm trying to show that a equals b to get my contradiction.
right.
That's what I'm trying to get. So I'm trying to use the fact that basically that I know, since I know a squared equals b squared, I need to use that to prove that a and b equal each other, using the fact that a and b are both positive. Notice it only works if a and b are both positive, because it could be the case that a is 3 and b is negative 3. Just because 3 squared equals negative 3 squared does not mean 3 equals negative 3. So I'm using the fact that I know that they're both positive, yeah, and the fact that their squares are equal to each other to show that they are equal to each other. So I could just use the fact that a squared equals b squared to say therefore a equals b. Make sense? Anyways, so I know that this product equals 0. What does that mean if this product equals 0? Don't make me walk all the way over here.
One of them is 0.
Huh?
One of them is 0.
Then one of these two is 0.
We proved that, like,
If the product of two numbers is 0,
all the way back.
then one of the two numbers has to be 0. So then, a plus b is equal to 0, or a minus b is equal to 0. But a and b are positive. So a plus b is positive. Using our positivity axioms, right? A positive plus positive is positive. Therefore, a plus b isn't 0. So what's 0?
A minus b.
So a minus b has to be 0. Remember, I knew that this is 0 or this is 0.
Right.
This can't be 0, so this has to be 0, which gives us that then a equals b.
Right.
Then a minus b equals 0, which gives us a equal b. Contradiction. Therefore, that has one and only one positive solution. And now we can define our square root symbol. When I say the square root of a number, 2, I mean the one and only positive solution to the equation x squared equals 2. Let me write that out a little bit more clear. The square root of y is logically equivalent to the one and only one. Let's see. How do we typically do this? We do it something like x equals the square root of y is logically equivalent to x squared is equal to y. The one and only one positive solution to this is what we mean by the square root of y. Do I have that backwards?
That's right.
No, that's right. Make sense? So this symbol's always talked about. So when I say the square root of 2, I mean the one and only one positive solution to this equation. That's what we mean by that symbol. So now we can define it, since we know that there's one and only one positive number that satisfies equations of squares like that. Make sense?
No, not really. Wait, how did we get that there's one and only one? Like,
So let's ignore the mess I made here, and we'll just write in terms of what we proved up
well,
here.
I mean, to get 9, you can either square 3 or you can square negative 3. Is that-
So, right, but now we're defining. So let's look at what exactly it says. So this says, pick any positive number c. Okay? Then, there's one and only one positive number x, such that x squared equals c.
Oh, there's only one positive number.
Right, so now when I say the square root of c, what do I mean? I mean that is equal to the one and only x in the positive real numbers. That makes this equation true. You'll notice in algebra before when you had something along the lines of, if I know x squared equals 4, then what did I say? Then x is equal to plus or minus the square root of 2. Square root of 2 is always giving me a positive number.
It's just 2.
And then,
Right.
oops, 4. Plus or minus 2, or plus or minus square root of 4. I just want to keep the number in there since that's how we have it written there. If x squared is equal to 4, then x is equal to plus or minus the square root of 4. But this part of the equation, square root of 4, is always positive.
Right.
And we just include, we might also want the negative case. So when I say the square root of a number, I always, if the number there is positive, c has to be a positive number, I always mean the positive solution to this equation. The one and only one positive solution to this equation is what I mean by the square root of a positive number. So now we can use that symbol and have it mean something. Okay, one more proof. And this one's going to be to prove that if S is bounded from below, then it has the greatest lower bound. We'll keep that there. We'll erase this, since we'll be using that axiom. And lower bound we have written up there. So we know what it means for a set to have a lower bound. We didn't answer questions, did we? Did we have homework questions?
Well, I figured it out after we went through some of this, and I went and did it on break.
So we're good?
I have one.
Okay, let's do homework questions real quick.
So number 2 and 3, I believe. I was just, so I did 2 and then realized that I did 3. Like, I didn't realize the difference between the two problems.
Between 2 and 3?
Yeah.
So 2, you were just saying whether it's false or true.
Oh, and I proved. And then number 3 was proving that there was
And then-
one and only one.
3 was doing a proof, but it looks like, oh, sorry, I'm looking at 1.1. I am looking at wrong exercises, sorry. That's future homework. Exercise,
Appendix A.
so you're saying 3?
2 and 3.
So 2, the multiplicative identity is unique,
Mm-hmm.
okay? 3 is for all A in R, A inverse is unique. The multiplicative identity is 1.
Oh.
Okay. So there's only one element in the real numbers.
So I was proving that 1 was unique in 2, and then I was proving that the
A inverse
like,
is unique.
egg-
Yeah, x to the minus 1. Yeah.
that makes perfect sense.
Okay. Any other questions on homework?
Did I do the wrong problem?
All right, that's a no. So let's move on for our last proof of the day. And we're done with 1.1. Okay. Proof. If S is a non-empty set bounded from below, it has a least or greatest lower bound. And from here on out, we'll refer to that greatest lower bound as an infimum. All right, 1. Let A equal the set of all x such that negative x is in S. So this is going to seem kind of weird. Let me go over a picture of what we're doing and then it'll make more sense. So I've got some set that I know is bounded from below. So let's pretend that that's a set that looks like this and then goes off this way forever. Something bounded from below. The idea of my proof is I'm going to construct a new set from it by reflecting it across the x-axis, or across the where you typically call the y-axis, to a set like this, show that this set has a supremum, and then therefore this set has an infimum.
Okay.
That's the big idea of the proof. So I take this set, turn it into this set, show that this one's bounded from above, therefore it has the least upper bound, therefore this thing's bounded from below and has the greatest lower bound.
Is that the easiest way to do it?
That's the way I did it, which is probably always an easier way to do it. Alright, so let A be the set of all x such that negative x is in S. That's flipping it like this. If this is S, here's my A. Make sense? Good? I'm assuming S is already defined as up here. I didn't specify that in line 1 like I should have.
As like.
Yeah. So let S be a non-empty set bounded from below. That's what S is. Now, line 2 is line 1. Okay. Oh, let that, comma, and let B be a lower bound of S. I know S is bounded from below, therefore it has to have at least one lower bound, namely B. Good? 2. Let X be any arbitrary element in A, and since B, say B but write X, and since B was less than or equal to negative X, that gives me X is less than or equal to B. So let's make sure we understand this. Grab something out of A. Remember that A is just the negatives of whatever was in S. Every element in S, negative B is one of those, or negative X is one of those. Every element in S, negative X is one of those, is greater than or equal to B because B was the lower bound of S.
All right.
Okay, you made the connection here? And then, if B is the lower bound of every element in S, then it's going to turn out to be an upper bound for the elements in A. So, 3.
Wait, so are we reflecting it across the axis?
We're kind of reflecting across the y-axis, although that doesn't really exist on the real number line. We're reflecting across 0, is intuitively what we're doing.
So will negative B be the greatest lower bound? I mean, no.
Oh, sorry. I'm supposed to have a negative B here.
Yeah.
I'm seeing it one way. Thank you for saying that.
Okay.
I took this, multiplied both sides by -1
Okay. Yeah.
to manipulate this inequality. So in other words, B was less than or equal to negative X. Looking at this picture, what might a B be? Let's say that this is -10. Notice over here, -10 is the lower bound for the set that starts here and goes off to infinity. Therefore, +10, or negative B, is going to be an upper bound for the set when we multiply everything by -X. You following this? Okay. So X is in A, and since B is less than or equal to -X, that implies X is less than or equal to -B. Therefore, -B is an upper bound for A.
Right.
Therefore, A has a least upper bound. Is that the way I want to do it, or am I going to need to introduce a variable to make something make sense? No, that's how I do it. Therefore, A has a least upper bound. Upper bound, comma, call it C. Good?
And C can be equal to B, right?
Yeah. then I know negative b. Then c is less than or equal to negative b. Negative b, in this case, 10. Negative 10 was my b, so this over here is negative 10, in case the negatives are throwing you off. Negative b was an upper bound. Negative b was an upper bound. C is my least upper bound. The smallest thing that's still an upper bound of this set is going to be less than or equal to b. It can only be this way of b. So since negative b is an upper bound for a, I know, based off of the completeness axiom, that a has a least upper bound, called c. So c is the least upper bound. It has to be less than or equal to every upper bound. It's the least upper bound. Clicking. Then c is less than or equal to negative b, comma, and so b is less than or equal to negative c. Obviously, the negative of the c is going to end up being my infimum, right? But let's tie it all together. 6. So tying the x's now. Also, x less than or equal to c less than or equal to negative b gives b less than or equal to negative c less than or equal to x.
Negative x.
Negative x, thank you. So that's tying in the x's into our equations. So I know c is less than or equal to negative b, but I also know c is greater than or equal to every x, because it's the least upper bound on a. X is the element of a. So c is greater than or equal to everything in a, and c is less than or equal to negative b. So that gives me negative c is less than or equal to negative x, and b is less than or equal to negative c. Remember, negative x is the element in s. X is the element in a, negative x is the element in s. C is bigger than everything in a, negative c is less than or equal to everything in s. Negative c is bigger than every lower bound, the same way that c was less than every upper bound. So, negative c, this is exactly what we mean by the least upper bound. It's an upper bound, or the greatest lower bound, sorry. Negative c is our greatest lower bound. It's a lower bound because it's less than or equal to every negative x. It's less than or equal to everything in s. And it's greater than or equal to every lower bound. Are the negatives throwing you off?
Negative c is greater than or equal to b?
So let's go back on our picture here and let's just get rid of numbers and put in our letters to help see the argument.
Okay.
Okay, so the set up here was the set S. The set down here is my set A. My lower bound for S we called B, which made negative B an upper bound on A. You follow that so far? Now since A has an upper bound, it has a least upper bound called C, which makes negative C the greatest lower bound over here.
Why can't we just keep
This
going?
set contains all our negative x's. This set contains all our x's. So our x is less than or equal to c is less than or equal to negative b, gives us our b is less than or equal to negative c is less than or equal to negative x. That's these two inequalities.
Okay.
So the negatives are just naming, flipping back and forth between our two sets, but
Why can we just say, because S has a lower bound, then it also has the greatest lower bound.
that's what we're proving. We
Why-
can't use that to
Why
prove
didn't we
it.
prove it the same way that we proved A as an upper bound? I mean, a lower bound. No, that's an upper bound. Right. We spent, like, we went and proved that A had an upper bound. Shouldn't the proof be pretty similar to S as a lower bound?
We proved A has an upper bound.
It's an axiom, isn't it?
we use the fact that, look, we defined A in terms of S. So we knew that S had a lower bound.
Well, what I mean is, the last proof we did, didn't we prove that a lowest upper bound exists?
For the square root problem?
For any proofs we did today. Didn't we prove that, in one of the proofs we did, didn't we prove that any set that has an upper bound has a
Least upper bound?
least upper bound?
No, that's
Or-
the axiom. This is the first proof we used that axiom.
So we just assumed that was true, and then we're proving that for the other side.
Yeah.
Okay.
In other words, we don't need a second axiom that says for every set that's bounded from below, it has a greatest lower bound. We don't need that as an axiom because this axiom gives us that.
Right.
But that's time, so we'll call it there. We finished 1.1. So next time you can turn in your appendix homework in 1.1.